not connected. Well, apparently they know what I like to do, so they disconnected the speaker. Okay. That's okay, I'll bring my own next time.
There you go.
They make these small, tiny little boom boxes that are battery operated. And the sound quality is really quite impressive, given the size of the thing. They are still putting out pretty good, quality, bass and mid. They don't sound too tinny. Alrighty, well, I think the recorder is on. We'll double check because that's important. I just closed the monitoring screen, but we'll double check. Yep, so the recorder is on. We'll go ahead and get started with this class. Are there any questions from the previous topics? Are there any questions about half adders and full adders? No questions? Okay, so I just want to kind of remind you guys, how everything is connected, about all the stuff that we have talked about. Okay, so when it's in full screen mode, my application tab actually won't show up. All right, so I'm just gonna use mousepad to kind of textually, demonstrate, what we have talked about so far. So on the first day, we talked about vacuum tubes. You don't have to write this down. I'm just, doing a little quick recap here. To transistors, to ICs, okay? But basically, an IC is still based on transistors. It's just that we are packing a lot of transistors onto the same area, okay? So it's just an advance of technology, but in principle, nothing has changed. So, and then the next slide, talks about a small circuit. So we made a NAND 2 gate out of 4 transistors, okay? The exact type of transistors you don't have to remember. This is definitely not a electrical engineering class nor a computer engineering class. For those of you who want to get into EE or CE, you will definitely see this stuff again. Okay, but we made a single NAND gate out of 4 transistors, and those 4 transistors consist of 2 N-channel MOSFETs and 2 P-channel MOSFETs. Okay. Once again, this is not really that important. What is important is understanding that this is a very important transition, because from devices, from transistors, we are now turning into logical operations. Because a NAND 2, which is the negated version of a conjunction, is a logical operation. You can do that in C++, okay? Put a not on the outside, and in parentheses, you use ampersand, ampersand. So we are now bridging from hardware back to all the stuff that we are familiar with from cisp310, which is basically logical expressions. Are we doing okay so far with this transition here? This is just a quick recap, but it is important that we can make this connection. Okay, so NAND 2 gate doesn't seem very important, because who would use a negated NAND, a negated conjunction in C++? Well, if that is the only thing available to you, you can use it to imitate all of the other logical operators that you're already used to. Regular negation, easy, okay? Regular conjunction, easy. The only one that is a little bit harder is regular disjunction, because you need to use De Morgan's law to get to that, okay? So that's where we went with that slide. NAND to regular NOT, to regular OR, and regular AND. Okay, so we made that transition. So now we have all the same basic tools that are the basic logical operators that we have learned to use in cisp300 and also in 360. But, well, that's all useful, but what about calculations? What about doing calculations like adding 2 numbers, okay? So then we took a detour to talk about what is a value as opposed to what is a number, okay? A value is nameless, okay? It is just the amount of the number of things that you can see, that you can touch, that you can feel, that you can measure, and so on. But it's not a word, okay? There's no representation. The representation of quantity are numbers, okay? So when we see a number like this, it is a way to convey the amount, the quantity, which is 250, if this is a base 10 number, okay? this can easily be a base 16 or hexadecimal number. If it's a hexadecimal number, what is the quantity being represented? We have 0 of 1s, we have 5 16s, and then 2 of 256s. Okay, so you add it together, it will be 512 plus 80 plus 0 in base 10. Okay, so that would make 592 in base 10. So this is base 10, this is in base 16, but they are representing the same quantity. Are we doing okay so far with all of this stuff? Okay, so we took a detour to talk about base conversion, in particular base 2, because base 2 is what is important inside that box. A transistor is either on or off. Okay, so it's binary in nature. That's why we have to understand how to do everything in binary. So now we have two paths, okay? Because one path talks about logical operators, the other path talks about number representation, in particular binary. But those two paths merge again when we talk about, okay, let's talk about how to add numbers in binary. Okay, was it difficult?
No.
No, because it's so easy because you only have 4 cases for each basic operator, okay? You have, for addition, you have 0 plus 0, 1 plus 0, 0 plus 1, and 1 plus 1. 1 plus 1 being the only one that is a little bit tricky because the answer of 1 plus 1 is a 0 with a carry of 1. Okay? So we made a table out of all of those things, and then we say, can we do this but only using logical operators? And we found a way to do it. Okay? So we were able to build a half adder using just basic logical operators, and then we use half adders to make full adders, and then and that's basically how we bridged from logical operations to half adders and full adders, and then we can do calculations, which is the most important part inside the processor. This is all inside the ALU, or the arithmetic and logic unit inside the processor, is the one that performs all the addition, subtraction, multiplication, and so on. All right, so this is a quick recap of where we have been for the past week or so, and where we are going. We will take a look at subtraction, and then we'll also take a look at rationale of this class. Why do we have to learn to program in assembly? It seems like it's a waste of time because it should not be needed. Okay, so that's kind of the focus of today's class. Back to Moodle, I would like to point out where we are currently at. We are now done with half adding. We'll talk about half subtracting and full subtraction a little bit later. It's not that much different, okay? That's pretty easy stuff. But we'll also take a look at the Linux tool chain and GCC. In other words, how do we write programs in this class? So I'll give you a quick preview of that. You won't be doing that until much later, okay? At least 5 or 6 weeks. We won't be actually writing programs in assembly. Instead, what we'll be doing is to use LogicSim to make a processor, to make enhancements and modifications to a processor that I have designed. But I will also demonstrate debugging using GDB, and also show you a few buggy programs. And some of these may have symptoms that will be almost impossible to figure out unless you know how to program in assembly. So that's the rationale of why you really should take this class. Not only because it's the requirement to get my transfer degree. That's not a good reason to take a class. Well, I mean it is, but it's not, right? Because then you won't be actually getting the material and related to stuff that you actually need to know. All right. So what we'll do is we'll go ahead and get started with subtraction first, okay? And then we'll move on to those example programs. Oh, by the way, I also have assigned a new due date for the lab activity LogicSim, because last time I said I would change the logical expression and then tell you guys that it has been changed. It has been changed, so the due date is 1 week from today, okay? Which should be plenty of time. Oh, the other thing, one more thing. Okay. I keep forgetting stuff. Okay, in LogicSim, there's a built-in tutorial and help. Okay, so let me just show you what it looks like, because I think you should know that it is available, because it is actually pretty good. I am impressed by the built-in help of this particular program. A lot of times with special programs like these, people don't spend the time to do any type of online help, but this one is exceptional. Okay, if you look at the tutorial, it gives you step-by-step instructions of how to do something. In fact, I would say I need to read through this entire thing, because I know how to use LogicSim to the point where I can do all the things that I need to do. But when it comes to all the features and all the stuff that LogicSim can actually do, I think I'm using maybe 10% of what the application program is actually capable of. Okay, so I would point out to you that this is really helpful. You can also go take a look at user's guide. Okay, so the user's guide is, it's the same screen, is it? No, it's not the same thing. It's different from the previous screen. So this is actually pretty good. If you have time, I would go ahead and read through this. Or if you cannot figure out how to do something, try to refer to the online help and see if you can find the material in the online help. Because one, you don't have to wait for somebody to respond back to you. And two, a lot of this stuff actually relates to this class as well. Okay, so it's actually not a bad idea. Are there any questions at this point? No questions? All right, if there are no questions, we'll deal with subtraction, okay? Binary subtraction. And just like with addition, well, I'll let this one stay, because at some point I'm gonna do something with it. So we'll go back to my mouse pad here. So we'll go ahead and deal with subtraction, binary subtraction. So the notes is already online, so you can actually just look it up, subtraction. All right, so binary subtraction is not difficult, but before we go to binary, we'll deal with decimal first, okay? So in decimal, what is 1 minus 5 in decimal? -4 is one answer, but if you want to carry out multi-digit subtraction, what is the other way to look at -4?
It's 0 with a remainder of...
No. After you borrow from a 10, what do you have? If you borrow 10, then you have 11 total, right? So you subtract 5 from 11, what do you get? You get 6, exactly. So you have a 6 and a borrow from the next digit. I know I write it in a funny way, but it's actually, it will come in handy later on. Okay? So this is how we look at subtraction in base 10. 1 minus 5 is 6 with a borrow of 1. Is that okay? No? Yes? Kind of?
Yes.
Yes? Okay. Then we can move on. All right. So another example, just to be sure that we know how this works. Okay. 6 minus 2. Okay. 6 minus 2 in base 10 will give you a 4 with a borrow of 0. Okay. It's just a funny way to write something that you already know. Okay. Are we still doing okay so far at this point?
Yes.
All right. So now let's deal with binary subtraction. Okay. Oh, by the way, how many cases of these things do we have in base 10? There are 10 digits, right? So there are 10 digits being subtracted from, 10 digits to subtract from the other one. So the table is technically a 10 by 10 or 100 item table. Now most of you go like, yeah, but a lot of those is actually pretty easy, right? Because the number subtracting itself is a 0, okay? Any number minus 0 is the number itself, and the table is, well, in this case, it's not symmetric because subtraction is not commutative, okay? But you still have a pretty good sized table. Anyone with a younger sibling who's going through 2nd grade, or with your kid going through 2nd grade, will understand, it takes a while for a kid to remember all the subtraction rules. Okay, it's not something that can just be picked up and go, okay, it's done. Okay, all right. So let's take a look at binary subtraction now. Well, with binary subtraction, we only have 2 choices for the top digit and 2 choices for the bottom digit. So we only end up with what? 4 possible cases. Okay. So let's deal with 0 minus 0 first. In base 2. 0 minus 0 in base 2 is 0 with a borrow of
0.
Okay, very good. How about 1 minus 0?
1
is a 1 with a borrow of
0.
That's independent of the base, by the way, right? Because 1 is 1 in any base, 0 is 0 in any base. Let's deal with the next one. 1 minus 1 is a 0 with a borrow of 0. So the only one that is going to be a little bit tricky is 0 minus 1. Well, since 0 does not have enough quantity, what do? We borrow. But what is the quantity that I'm actually borrowing from the next digit?
2.
It is representing a quantity of 2. So now I have 2. 2 minus 1 is 1. Okay? So that's basically what it is. It is a 1 with a borrow of 1. So when you look at these particular this particular table, not a table, but cases of binary subtraction, are there any questions? No questions? Okay. So we'll do an example. Okay, we'll just deal with some actual concrete numbers and try to figure out okay, but how do we use all of these things in a multi-digit subtraction? So we'll go ahead and do a 1011 minus 0110. I think that should test almost all of the cases, not all of them. Enough. Okay, just like with addition, we have a separate row for the borrows. Okay, that's the way I write it. With a text editor, this is pretty much the only way I can do it. Okay. All right, so let's go ahead and deal with this particular subtraction case. What is 1 minus 0? It is 1. Okay, very good. So we put a 1 here. Do we have a borrow? No. Now, if you don't have a borrow from the first subtraction or the subtraction between the first and the second row, I wouldn't put a 0 here just yet because there's a second chance to get a borrow. But in this case, obviously, we do not have a second chance because we are subtracting 0 from 1, which is 1 with no borrow. So if both subtractions are not yielding a borrow, then you don't have a borrow from the next digit. Okay? 1 minus 1 is 0 without a borrow. 0 minus 0 is 0 without a borrow. So neither is giving me a borrow, so the borrowed from the next digit is going to be a 0. 0 minus 1 is a 1 with a borrow. Now, if you have a borrow, you can just write that 1 right away. Because just like with addition, only one of the 2 subtractions can yield, only up to 1, I should say, only up to 1 of the 2 subtractions can yield a borrow of 1. So if you spot 1 that is giving you a borrow of 1 already, just write down a 1 because you are going to borrow. Okay? Now we can finish this one. 1 minus 0 is a 1. And in this case, 1 minus 0 is a 1 without a borrow. 1 minus 1 is a 0 without a borrow. So we have a quote-unquote dangling borrow flag here. Okay? It doesn't seem to be important, but it is. Okay, so we're going to keep track of this kind of dangling borrow flag, just like we did with the carry flag. Are there any questions about this particular calculation? Yes?
Can you explain 0 minus 1?
0 minus 1 needs a borrow because 0 as a quantity does not have sufficient amount to subtract 1 from, right? So what you do, you say, okay, I don't have enough money. So you go to the next guy and go like, hey, do you have a 2? The next guy is a 2, right? Or twice the amount of you, right? So that guy go like, okay, fine, you'll take this. So suddenly you have a 2. 2 minus 1 is a 1. But how did you end up with enough quantity to carry out that subtraction? You borrow from the next guy. So now you have to set the borrow flag so the next guy knows, oh, somebody borrowed 1 from me. So if that guy ends up not having enough money, then he will have to borrow from the next guy and so on. It's not different from base 10 subtraction when you need to borrow. Are there any questions about binary subtraction? Yep. You first and then you. Okay, go ahead.
Okay, in your example, you have a dangling 0.
Yep.
What if it were a 1?
Then you put a 1 there.
Okay.
The bottom, but that's a good question, okay? Because what we're trying to do is we are fixing the number of digits of how we represent numbers. So in this case, we are only using 4 bits to represent numbers, and that's why the two numbers that we are operating on are 4 bits, but the result is also only 4 bits. And the dangling borrow does not belong to the number, does not belong to the resulting number. It is just dangling out there. And go ahead.
So when you borrow, the next number is always 2, even though...
It's always twice the amount. It's just like in base 10, the next digit is, when you're borrowing, you're always borrowing 10. Except in base 10, you borrow 10. In base 2, you borrow 2. In base 7, you borrow 7. Because you're borrowing, you're asking the next guy, go like, hey, you got $1? But it's not $1, it is 1 unit. And the next guy is always measuring things that is 7 times if you're using base 10, 7, 10 times when you're doing base 10. So that's basically what it means. If you really want a good analogy, it's like, okay, look at a row of people, okay? So you have, $1 bills, you have $10 bills, you have $100 bills, and you have $1,000 bills, okay? So when we're doing subtraction and he doesn't have enough money, what does he do? He asks you to borrow, right? He borrows from you. So you basically go like, but you have $10 bills, right? So when he borrows a single bill, he's borrowing $10. But when you don't have enough money doing the subtraction, you borrow from the next guy, but the next guy only has $100 bills. So whenever you're borrowing 100, and so on. Are there any other questions? Yes?
So, but doesn't that dangling flag, if it's a 1, change the value of our, shouldn't it add some sort of value to our result?
When you look at the actual resulting value, yes, okay? But what it means, if this is a 1, it means you don't have enough digits to represent the result. We'll deal with that later. But mechanically speaking, this is all we do. We just put a dangling thing here. Any other questions? It doesn't seem easy. It seems a little harder and awkward compared to base 10. And that's only because you guys have, 18, 20, 30 years of experience using base 10. And suddenly we introduce base 2. And that's why something that is supposed to be a lot easier seems harder. That's just because we're so used to it. And why do we have base 10? Stupid reasons. Because we got 10 fingers. That's all. Because if they had chosen base 2 to begin with, we would have been so much better off with computer science and a lot of other stuff. Base 10 really does not help. They cannot count a thumb and make it base 8, and that would still be a lot better. I think octopi, got this advantage on us. If they are not so short-lived, they probably have civilizations that are exceeding ours. Alrighty. So, but that's calculation. That's based on value and quantity. So now the question is, can we use logic gates to do all this? Okay, just like we did with addition, now we want to do it to subtraction. So what we want to do is to make a table. Okay, so the table looks like this, x, y, and we say, what is the result of x minus y? Okay, so we'll just say result of, x minus y. And we now also want to take care of the borrow of x minus y. Does the calculation of x minus y need to borrow from the next digit? If there's a next digit, right? Okay, so we'll enumerate all 4 possible cases. We got 0, 0, 0, 1, 1, 0, and 1, 1. When you subtract 0 from 0, the result is just a 0 without any borrow. When you subtract 1 from 0, that's the only tricky case because the result is a 1 and the borrow is also a 1. When you subtract 0 from 1, the result is a 1 without the borrow, or the borrow is 0. When you subtract 1 from 1, both the result and the borrow are zeros. Are there any questions about this table and how it captures all the individual cases that we have demonstrated a little bit earlier? It just makes it easier to read. Okay. Are there any questions about this step? No questions? Yep. Okay. All right. So what we're going to do now is to say, can I use a logical expression and come up with the same column? Can I use another logical expression and come up with this particular column here? Let's focus one thing at a time, just one thing at a time. So what I'm going to do, which is going to be a little bit harder for you to do on paper, but that's why I'm recording this, is to copy and paste, just remove the other column that we are not paying attention to. So we'll just go ahead and focus on the result of x minus y. For those of you who paid attention in class or studied, you will say, we have seen this before. Addition has exactly the same thing. The result of addition has exactly the same column, 0, 1, 1, 0. So do you remember what we did? Okay, it's not a really easy, expression, but if you just want to use not, and, or, okay, not using exclusive or as an operator, yeah?
Is it not x and y, or
Yeah.
x and not y?
Yep, exactly. That's it, okay? But you don't want to just take my words for it, just double check. Since in this case x is a 0, not x is a 1, y is a 0, so 1 and 0 is a 0. On the other side, x is a 0, 0 and whatever is a 0, so in this case it's definitely a 0. In this case we have x being a 0, not x is a 1, but y is a 1, 1 and 1 is a 1. Now in a disjunction, if one thing is a 1 already, it's already a 1. So we know for sure this is a 1. This is really just a symmetric case of the previous one, because in this case x is a 1, so we look at the second expression. Since x is a 1, y is a 0, not y is going to be a 1 as well. 1 and 1 is a 1. Since one side of an OR is a 1, the whole thing has to be a 1. The last case is having 1 as in x and also y. So that means in either conjunction, one of the component is going to be a 0 because of the negation of a 1. So that means the whole thing is going to be a 0. I just kind of shortcutted the evaluation of the expression. You can do it on your own in details to double check and make sure that this logical expression will do exactly the same thing as the result of binary subtraction. Now, this is an important moment because once again we are bridging calculation, arithmetics, and logic gates. Okay, this is how we implement components inside the ALU to actually perform calculations. Are we doing okay so far with this one? All right. So the next one, which looks kind of like awkward because, hey, how do we do the borrow flag? Okay, so I'm just going to get rid of this one here so we can focus on just the borrow flag here, or the borrow bit. That's just awkward because and is not going to do this, or is not going to do this. But there's one simple, well, I wouldn't say really simple, but it's not really that difficult. But one expression can do this just fine. Whenever you have only one thing that is a 1 in a column, it's actually very easy because you just need everything else to go to 0. So in this one, we'll just say, hey, what about not x and y? All by itself, okay, it is the same it's the same thing as the first component of the disjunction of the result, but we'll double check and see if this works, okay? X and y are both zeros. Well, since y is a 0 and is in the conjunction, the whole thing is going to be a 0. All right, this is the only one that should end up with a 1. Let's see whether it does end up with a 1 or not. X is a 0, not x is a 1. Y is a 1. 1 and 1 is in fact a 1. Okay, that seems to work. But we'll check all the other ones too, because when it's supposed to be a 0 and we get a 1, that's not going to work. So in this case, x is a 1, not x is going to be a 0. since we have at least one 0 in the conjunction, the whole thing is going to be a 0. And we can apply the same reasoning here, so the whole thing is going to be a 0. So you can see the two columns, the borrow of x minus y, exactly matches up not x and y. Guess what? We'll just go ahead and use that logical expression to implement the logic to come up with the borrow flag or the borrow bit in a binary subtraction mechanism. Are we doing okay so far with this? All right. So you already know enough to actually do your homework assignments. The adder and the subtractor homework assignments, they're on Moodle, they have not been assigned, but you already have enough knowledge to work on those. Okay, I'll show you the steps of working on those things a little bit to the end of this class, maybe eating a little bit into the lab time, okay? Any other questions? No other questions? All right. So if there are no questions, I'm going to shift gear a little bit here, and we'll start to talk about, why. Yep, go ahead.
Will sheet.
Thank you. All right. Go ahead. And I have sent out messages to people who are on the wait list, with your permission numbers. Did anyone get those permission numbers? Okay, very good. Just want to make sure. And, well, since you're in 310, you should know this already. If you're on the wait list, you have to drop yourself from the wait list first before using the permission numbers. In cisp310, which is the first class that many people take, there's a great deal of confusion because people, do not understand. They have to get out of the wait list first to use a permission number. All right. So a few things. It will be helpful to go through this first. Okay, how to use the tool chain. This is actually borrowed from my C++ class, but it's going to be about the same. Okay. All right. So you can read through this stuff here. You should have read through this stuff. Okay. But if you have not, I'm just going to do it, in the demonstration. So we'll go ahead and just use the demonstration. Just borrow one of the command line interfaces here. Many of you have taken at least one class from me, so you're somewhat familiar with the use of a command line interface. For those of you who are new to command line interface, it simply means instead of clicking stuff, selecting action from the menu, you have to type the command to do everything. Okay? It seems really backwards. Okay? It seems like, hey, this is 2015. This is not this is not the 80s or the 70s. Why are we still doing this? Well, why?
Why not? Less resources being used.
Few resources is being used, and if you want to work from home and your bandwidth is limited, this allows you to work, over a simple low bandwidth connection to a development server from home. Okay, your cable connection or your DSL connection can be down to, I don't know, maybe 50 kilobits per second, and it will still be usable. Okay, you try to run a GUI program remotely using a 50 kilobits per second type of connection, and you tell me which one is easier. Okay. So this is a big reason why command line interface is still useful. If you use code blocks or any of those GUIs on top of GCC or G++, this is still what is happening in the background. Okay. I really do not like to use code blocks because it has too many things you have to worry about. Every single menu has a lot of items, okay? And there are tons of options to do the compiling, linking, and whatnot. This way, it is limited, and you have to type out everything so that it forces you to understand how things are actually done. Okay? So we'll go ahead and start with a program. I will start with a program that will be used later on, so that at first it's working, and then we'll break it so it won't work anymore. Okay? There are two editors built into the virtual machine that you are using. One is VI, the other one is Nano. You can use either one, whichever one seems to be easier, you can just use that one. I use VI myself. So we'll go ahead and create a folder. mkdir is the command to create a folder or to create a directory. So I'm just going to create a folder called messed up. Okay, messed up. Okay, because I'm going to make a program that is messed up. Okay, but not in the usual sense. It's going to be messed up so badly that if you give the program to someone who only knows about C programming, they will not be able to tell you what to do with only the symptoms. Okay. So to change to the folder, you use cd. cd stands for change directory. Okay, so these are fairly commonly used commands in Linux or any type of command line interface. Even in DOS, even in Windows, these commands work. All right, so now I'm inside this folder, and you can see my current working directory, which is a part of the prompt, is reflecting that we are currently in that folder. So that means unless you supply the full path to a file, if you just say a particular name, it is assumed to be in this particular folder. That makes things easier. Okay, you don't have to type as much. So when I say vi, and I'm going to create a new program to do this, so I'm going to say, program1, proc1.c. Okay, we're just dealing with C, not C++ here. That means the file proc1.c is going to exist in this working directory, which is messed up. Messed up is the name of the folder. The folder itself is not messed up, it's just the name. All right, so this is VI. I'm not going to teach you guys how to use VI. If you want to learn how to use VI, just Google it, okay? VI tutorial. Tons of those things will pop up. Many YouTube videos will show up, so that is your responsibility. Pick one. If you choose to learn VI, I think it's a good way to get into programming, because a lot of servers and a lot of environments would use VI. But if you don't want to spend that time, you can use Nano. You can use other tools. So I'm going to write a very simple program here. Pound include stdio.h. We have a void function f. Doesn't do much except it prints in function f. That's all it's going to do. We have a function g here, printf in function g, like so, and then we have our usual entry point of the entire program, which is main. So we're going to call one of the functions, let's say g, and it's going to return 0. This is my entire program. Okay, so what do you think this program is going to do? And exit, right? That's all it's going to do. Okay, so let's go ahead and check whether that really is what it's going to do first. So to exit from VI, do a :x. And the first step is to compile the program. In case you forgot, what compiling is, it is a translation. Okay, we are translating from the high-level programming language C to machine code. Okay, which is stored in the object file. Do you guys have any questions? Any questions related to this? No? Okay. So the first step is to do a GCC. Now with GCC, you can supply a lot of different flags. I like to turn on all the warnings. Okay. Pedantic, which makes sure that your code is NC compliant. So you're not going to use any feature that is unique to GCC. In this case, I want to turn on -G, which is a debugger option. -G makes sure that later on we can use GDB to debug a program. Okay, but I'll just, for now, we'll just say that it is important. And then we have a -C to mean we just want to compile. Okay, we are not linking, we're just compiling this particular source code. And then you supply the name of the program, the source code, press the enter key, there's no problem, everything is good. When you do a ls, which lists the current content of this folder, now we have two files. The .c is the source file, the .o is the object file. The object file does contain the equivalent machine code for this program, but it's not ready to run. Okay, we cannot run the object file. Why can't we run the object file?
Have to link it.
You have to link it, but why do we have to link it? The object file does not contain everything that we need to run the program. Why not?
There's a separate header file.
There's one function that I call that I do not define. Which function is that? printf, exactly. So if proc1.o is simply saying, hey, I need to call printf, but nobody is defining printf, it's not ready to run. So that's why we need to link link object files to create the executable file. So gcc-o proc1 -o means the following name is the name of the output of this linking process. So I'm just naming the executable proc1 without any extension. Then you supply all the object files. Now in this case I only have one object file, which is proc1.o. What the linker is going to do is to go through the object file and say, do we have any unresolved references to other functions? Oh, we got a few here. Okay, we got printf, and there are a few that are actually quote unquote hidden. Okay, because the entry point of a C program to call main is also something that is entirely missing from my own program. So the linker will get all of these things from what we call the standard C library. So it will link all those things in, mix it up, and go like, okay, now we have something that does work. Okay, so press the enter key and do another ls. You can see now there are 3 files. Proc1 in lime green is actually an executable. This is how highlighting is used to highlight things that can run as a command. So proc1 can run all by itself now. Are there any questions about the differences between compiling and linking? No questions? Okay. All right. So let's go ahead and run this program. Proc1. Well, doesn't work. Well, it doesn't work for a very good reason. In Linux, just like in Mac OS X and many other operating systems, they maintain a path system variable. This is the path system variable. So when you run the command, when you just type proc1 and then press the enter key, what bash, which is the born again shell, okay, what it's going to do is to look through these folders. There are 5 folders they will look through for that particular name, proc1. Okay? Well, proc1 does not exist in any one of those 5 folders in the path variable. So what is it going to do? It'll go like, I cannot find it. But it's right here in the folder that we are in. Well, do you see the current folder or the current working directory, which is represented by a single dot, a single period? Is it part of the path? It's not. So it's not going to be able to find it. So for anything, for any executable that is outside of the path directories, you have to specify the actual path to it. Since it is in the current working directory, which is represented by a single period, we say current working directory / is just a separator. And now you can spell out proc1, run it, and it just prints in function G, and it's done. Okay? So that's kind of the general workflow of how to create, how to compile, and how to link a program using the command line interface. Okay? And I'm pretty sure someone is thinking, I just want to click the run button and be done with it. Well, you can do that when you are at work. But in this class, this is how we do it. Yep.
So when you were, for your line for the linker, the gcc.o proc1, that proc1 is just the name of the executable that you gave it.
That is correct. You can name it anything you want. You can name it like proc1.exe, proc1.run, proc1.out. It doesn't really matter. The only thing you don't want to name it is proc1.c, because that's going to overwrite your source file. And well, it happens to people a few times, and they learn the lesson, go like, I'll be extra careful not to overwrite my source file. Alrighty. Well, this folder is called messed up for a reason, because I am going to mess up the program. Okay? So we'll go to proc1.c again, and we'll find a way to mess it up. So what I'll do is I'm going to put a int x4 here. Okay. So what does that mean in C++ or in C? It's common to both C and C++. What is x?
An array of integers.
An array of 4 integers. Okay. So in this case, an integer would be 32-bit wide because I'm using a 32-bit platform. Okay. So what I'll do is let's not mess it totally first. So we'll say x let's turn it into chars. Okay, so char is actually more fun to play with. So we'll just go ahead and say x bracket 3 is 0x 9c. Okay, 8c. Okay, that's not going to break the program because x bracket 3 does exist. Okay, this is an array of 4 elements, and x bracket 3 turns out to be the very last of those 4 elements. Okay, so this program will compile just fine, it will link just fine, it will run just like normal, right? So we'll go ahead and confirm all of that stuff, but without typing all those commands again, because you can use history. So history is really handy because when you just type history, it will show you all the commands that we have run, today and also before that. And you can just refer to the number of the command that you want to run again. So the first thing we want to do is to compile, which is at 100. And then the next one we want to do is 101, and that's 101. And the compiler is pretty smart. It's telling me that variable x is set, which means I put the value into it, but it's not used. Okay, so I put something into it, but I never refer to it ever again in the subroutine. Is it an error? No, it's not an error in any way. The program is going to behave just fine. However, it is not going to work correctly. Okay, it's indicative of that might be a problem. Okay, in an actual program, it is indicative that might be a problem. I did not get the other command right. It's 102 to relink the program. So now that we have recompiled and relinked, we can run the program again, and it's like, oh, but that's boring. It's still doing the same thing as before. Okay, no big deal. All right. The next thing I'm going to do is to use GDB because I need to use GDB to get a clue of how to mess up the program so it will do something that is funky. Okay, so we'll use GDB. GDB stands for GNU Debugger. Okay, this is how we are going to debug programs in this class. Okay, and because we already compiled the program using the -G option, the debug information is in the executable already, which is really handy. GDB proc1. Uh-oh. I did not install GDB in this particular live distribution. Yours already have GDB installed. It's just that when I read work on the distribution, it's not there. That's okay. We'll just say install GDB. Now we have GDB. It's pretty easy. See, I don't have to use a browser or get out of the command line interface to install something. I like that. Okay, so now we can use GDB. And this is GDB, okay? It's really ugly if you have not used a command line debugger before. This is really ugly. It's awkward, it's ugly, and you have to learn the commands too. L is list. It shows you the source code of the program. And what I'm going to do is to put a breakpoint in function G. Okay, so I'll put a breakpoint in function G, which is starting on line 8. So B is for setting the breakpoint. 8 is the line number. So I'm putting a breakpoint on line 8 at this point. Then I can just run the program at full speed, and I'm inside the function G now, ready, just about to print the statement. But what I really want to know is not anything here. It's not even in X. What I really want to know is to say, oh, what is the address of this function? Okay, so I can say print the address of function G, which you can also do in regular C and C++. And I just want to look at this address and go like, okay, 14 is the last 2 digits. Okay, so I'm banking on a few things here. You can do the same thing with %f. Okay, that will %f, that will show you the address of function f, where it starts. Okay. All right. So we got a few things here, and I'm going to do something now to mess it up. Okay. So I'm going to quit the program. I don't have to finish running this program because I'm ready to mess up this particular program. So what I'll do is I'm going to change this to 2 statements. And obviously I forgot those numbers already. Did anyone remember? Nobody remembered. That's okay, that's why everything is recorded. I can actually look at the video file while it is still being recorded to look at what I just did, okay? Which is a very handy tool. So we'll take a look at today's note, 0901. Okay, so it looks awfully confusing because it is a replay of the beginning of this class, and I just need it all the way to the end. Where's the control of it? Okay, there we go. For whatever reason, the control is separated, so now we are close to that. Fast forward a little bit, There we go, function G, function F, oh, there we go, we got it. Okay, so it's 83FB. Okay, so let's go back to the other program. See how handy it is?
My head hurts.
Is all that recorded too? So is it like
Yep.
recording within the recording?
Yes.
Within the recording?
Yes, that is being recorded as well. The replay of the current recorded session is being recorded into the same video file. It's like time loop thing, you know. All right, so now we kind of know how to change this program. So I'll just write down those numbers first. Okay, one is hexadecimal 83. The other one is hexadecimal, I can't remember. FB, there we go. Okay, so FB is the other one. So now the question is, but where am I going to tweak this to make that, to make that change? Okay, so now I have to remember how things are organized within the computer. So I have to draw it because I cannot remember everything. So we got X, which is 1, 2, 3, 4. And that's a local variable, which is below OEVP. And then we got the return address right there. Okay, OEVP, return address. Okay, so we should be looking at, oh no, X is actually down here. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Okay, so we're looking at 10 and 11 here. This is going to be 11. This is going to be 10. Okay. Nope, they're wrong. This should be 9. It should be 8 because it's little endian. Okay. All right. So we're going to do just that, and I think it's going to mess up the program in some really weird way. Okay. It will crash, but before it crashes, it'll do something that makes it go like, eh? Or as my kids always say, what the? It's funny watching them play League of Legends. You'll just be screaming out, what the? Well, it's because you did not expect people coming out of the jungle, okay? Put the trinket over there. All right, so let's give it a try. And those numbers still work. And I think it's 100 and 102. 100 and 102. All right. So obviously I'm blatantly ignoring the warnings, right? It's complaining to me and go like, oh, this is overflow. This is not good. And go like, yeah. What do you know about programming? I teach programming. I know about programming. I'm going to ignore the warnings, right? So what do you do when you see warnings in your other classes? Not in this particular case.
Go back and fix it.
Yep, exactly. Okay, if the warning shows you something that is, oh, okay, I know what I'm doing. Mostly it is usually related to typecasting or something else where you can actually tell the compiler, yes, this is what I intend to do. Okay, so now the program is completely linked. We'll first go ahead and run this program all by itself first. It is still not messed up the way I want it. Did I miscalculate? Okay. 0, 1, 2, 3, 4, 5, 6, 7. So there would be 8 and 9. So 8, 9 should be correct. All right, I have to cheat a little bit here just to see how I can mess up the program. So we're going to put a breakpoint. The other way to put a breakpoint is by label. So BG is to set a breakpoint at the label G, which is the entry point of function G. Okay, so we'll go ahead and run the program. Now we're going to do something. We'll do something that will look like, wow, what is that? Okay, at this point, you can use that attitude, but later on, you will actually use these commands as well. No need to write it down at this point because I'm just getting the information that I need to mess up the program the way I want it. So we'll do something like this, and then we'll say that. Okay, so let me see if this makes sense. Okay, so there's X. This is ODBP. Oh, okay, it saved another register. So we're looking at 0, 1, 2, 3, 4, 5, 6, 7. So we're looking at 16 and 17. Okay. Okay, so I think I know how to mess up the program now. Aha! Okay. Okay. Other than the program crash, okay, which is a segmentation fault, what is so weird about this program? The behavior of this program. It went into function F, right? Because it printed the message that is only coming from function F, which is in function F. Okay? Now, obviously, you guys know which two statements are responsible for this because I've been working on it for, what, 10 minutes. Okay? But the question is why? The question is why did I, if I do something, okay, let me just show you the program first. Okay? So the question is why? It's not so much, you know, yeah, we know that line 12 and line 13 are responsible for the program crashing like that. Okay? We get that. Okay? The question is why? Okay, why making these changes to the array X is going to cause the program to crash in that particular way? We know that if you access an array out of bound, something that is not supposed to be changed is changed. Okay, we know that much. Okay, even in cisp310, I talk about that. Okay, memory corruption. The question is, what are you corrupting? Okay, and the corrupted thing, what is it actually used later on? You know, when you return, in this case, from a subroutine. Now, there are other weird problems too. Let me show you another weird one so that you guys can kind of appreciate, you know, the content of this class. Because the objective of this class, or at least half of this class, is to give you the tools to look at the symptom of a program, like what I just demonstrated, instead of, you know, going straight to the source code and go like, yeah, it's line 12 and line 13 responsible for it. You know the mechanism, so you know where to look. Okay, that is the objective. Let me show you another program that is kind of messed up as well, but this one is even more mysterious. Okay, so let's go ahead and write the other one. So we'll do a proc2.c. So this one involves void f, and f does not do a single thing at this point. I'm going to change that later. And then we have our usual main. Main has x, y, z as 3 variables, and we'll just kind of assign some random values into it. Not random, but you know, it's not important, you know, what they are. So y get -2, and we'll get z getting a value of 78. Okay, it doesn't really matter what the values are. And once again, the compiler will complain and say that, you know, I set the values of these variables, but I never really use them. That's fine, not a problem. So we'll call function f here. Okay. All right. So you can probably imagine this program is not going to be very exciting. Okay. Warn all. I'm not going to turn on pedantic because it's a simple program. -g-c proc2.c. And then we'll do the linking, which is gcc-o proc2 proc2.o. And we'll do a gdb, list the program, press the enter key to continue the listing. We'll put a breakpoint on line, I don't know, 14, okay? And run the program. So now we are just about to execute line 14, which is after the assignment statements and after the function call to f. What do you think is in x? 56, yep. Y has -2, and z is going to have 78, okay? No problem, okay? Cool, that's because I have not started to mess up this program yet. Now we go back and we'll mess up this program. And once again, I use an array of x. We'll just have 4 elements here. Oh, I know why we have that problem before, but this one is going to be a little bit different because we have 16 bytes using in x, and then we are 4 bytes for old EBP, so that should be x bracket 5 should do it. Okay, so this time we'll do something like this: x bracket 5 plus equal 4. Okay. Now, once again, we are accessing an array out of bound. I think it's just x bracket 4 too. And okay, so we know this is a bad program, okay, because x as an array only has 4 elements. But when the index is 4, it is actually trying to access the 5th element, which is not a part of the array. Okay? And how many people knew this kind of stuff from your cisp310 class? Okay, very good. So it will go ahead and change the location, some memory locations, okay, but it's not a part of the array. So it's going to trash or modify something it's not supposed to. So we'll go ahead and look at, okay, just going to look at history here. 127 is compiling and 128 is linking. And now we'll run the program. It has a segmentation fault. That's expected, okay, because I did trash up, mess up some memory locations. The question is, well, let's go ahead and look at closer look using GDB. This is why GDB is so useful, because it allows you to take a closer look at stuff. Okay, we'll put a breakpoint on line 16 again. If it does crash, most people would think, okay, because function f is the one that is modifying some memory locations that it's not supposed to, it's probably going to crash. Okay, we will not even get back onto line 16. Okay, but because of the way I did it, it will. Okay, so run. It actually got back to line 16. Hold on a second here. So what is crashing? Okay, the return 0 is crashing. That is actually true. But if you have any code other than just return 0 after function f calls, and you refer to variable x, y, and z, you're in for a big surprise. Let's go ahead and print those values. Print x, print y, print z. What does it look like to you? What used to be 56? What used to be 56? X, and now it's in y. What used to be -2? Y, and now it's in. Everything is shifted. The values of my variables are shifted. Okay? Now, why did it happen? Everybody can point to that one line that I wrote and say that's responsible. But the question is not where. The question is why.
Is it out of scope?
It is out of scope, but why is the program messed up this exact way? Go ahead.
The command kind of moved 78 to different memory location.
Nope, that's not what it did. It messed up one thing on the stack that is in control, that will influence how we access local variables. Okay? Now, what are the chances that you'll run into problems like this? It's actually not low. Okay? It is actually not low. Okay? Because the other one is a little bit crafted, but this one is not really that crafted. If you just look at the source code, this is it. I just accessed an array out of bound and add 4 to the element that I'm not supposed to be messing up with. The likelihood of something happening like this is pretty high, especially when you're in a loop, okay? It's not spelled out and say, I'm going to change x bracket 4 to something. Instead, you're saying x bracket I, you're changing to something, and I is a variable used in a loop. So now you have to look through the loop. What if the loop has 20 lines of code, 60 lines of code? Then it becomes really kind of difficult to track, what is the range of value of I, okay? But the problem is you look at the symptom of your program, okay? Now, this program obviously is not gonna work right. Even if there's not a return here, even if there are like 60 lines of code between the function call to f and the return 0 statement, all of those things will work incorrectly because the variables have shifted. So they will all be doing weird stuff, right? Because the values of x, y, and z are no longer the way they are. And then when you suspect something is wrong after function f returns, you look at the values of the variables. Everything is shifted by 1. Then what do you do? Where do you start when you look at the symptom and go like, well, this is weird, all the values are shifted by 1 into the next variable. And then what do you do?
Look at the index.
You
array
look up,
indexes.
but that's only because you saw what this program did, right? But what if this program called many other functions before you get to this point? You would have lost track of the symptom is showing up long after the cause of the problem. Okay? But what you should be suspecting is something has messed up a part of the stack. Okay? But what is the stack? Does anyone talk about the stack in cisp310? Do you? Okay. Does anyone talk about the frame pointer in cisp310? That's why you're here. Okay? That's why you're here. It is to equip you with the knowledge in case you run into weird symptoms in a regular C or C++ program. You would kind of at least have an idea of, yes, we know something on the stack is messed up. But from the symptoms, it looks like the frame pointer is messed up. Okay, now if the frame pointer is messed up, that usually means someone is accessing a local variable array out of bound, because that's the most common reason to make that happen. So what you'll be looking for would be local variables that are arrays and loops that can go through the array, and you see, okay, is this out of bound? Okay, did I do the bound checking correctly? Does the loop exit at the right time? Okay, so you would at least know where to look, what kind of problematic code to look for. Otherwise, you would not even know what to look for. Okay, your program is just kind of really messed up. It's just not behaving correctly. Okay, what is another objective of knowing memory organization behind the scenes? To write buffer overflow and stack overflow exploits. Okay, every successful hacker would have passed this class with flying colors. Because that's what they need to understand to write all the exploits. Okay? And script kiddie is not counted. Okay, those guys are just borrowing somebody else's code and go like, let me try this server, let me try this IP address. That's not it. Okay, people who actually craft exploits, those guys understand all of this stuff already. Are there any questions about what I have just demonstrated? Am I teaching you guys how to hack? Yeah, why not? That's the only way you can help to counter hacking. If you don't know how to hack, how do you counter hacking? Right? Question?
Okay. How did you get it to shift by 1? Is it that
It's the
highlight?
4.
No, what if that was plus equals 5?
Then it will be weird. Okay, plus equal 2 will make something that's really weird, because it's not shifting by one whole variable anymore. It's shifting by a half of a variable. So let's try this. Okay, And I'll let you guys kind of think about what's going to happen when I try to run this program this way. And we have compile and link. Okay. So when you run it without GDB, it's going to crash. Okay. It's not very useful when you just run it by itself. But when you use GDB to debug the program and put a breakpoint at the right place, which is line 16 here, then you have a chance to look at the variables. Just knowing the program crashes is not really helpful because you don't know where it crashes, why it crashes, and other symptoms that may help you identify the source of the problem. Using GDB gives you a chance to stop the program before it crashes, and then you look at the variables, x, y, z. Holy moly, they are way off, okay? Are they really way off? Maybe they're not. Okay, what do I see here? I see a negative 2. Fe is negative 2 in 2's complement. Okay, 2's complement, we'll talk about it in this class, okay? That is a way to represent negative values using only binary numbers. You're only using zeros and ones. This is how we represent negative values. That's why you're here, okay? I also see a 56 here. 38 in hexadecimal is 56 in decimal. Think about it this way. There are 8 ones and 3 16s. 3 times 16 is 48. 48 plus 8 is 56. So I actually see fragments of the variables, but they are not aligned correctly. Okay? This 38 should have in here. It should be FFFFFFFFFE. So this FE should have been here with all the other stuff being F's. So I can still see basically fragments of the variables that I should be seeing, but they're off by 2 bytes. Okay? So if I know the content of this class and I see this kind of stuff happening, I know the frame pointer has been messed up. But it's not like super messed up. It's not like somebody just jammed a completely random value into it. It's just changed a little bit. So I will be looking for plus equal to, minus equal to, that sort of thing, instead of just an equal to and then a whole different value. That is why I think this class is useful. It's not because I think many of you will actually program in assembly professionally in a career. Okay, very few of you, maybe 3 at the most, okay, will actually do that. But the rest of you most likely will have to debug C and C++ programs. This gives you the extra knowledge that you can utilize to debug tricky stuff in C and C++. All right. Are there any questions about why this is actually related to this class? No questions? All right. So with this out of the way, I'm going to show you. Oh, I can close VLC now. I will show you the homework assignment that will be assigned very soon. Okay, not yet, but really, really soon. One is a 4-bit adder, and the other one is a subtractor. Okay, the 4-bit adder, I'm not even going to bother, doing a whole lot about this, because if you just watch the video again from last Thursday, I just did it. Sort of, not completely, but I did a good portion of it. So what we'll do is we're gonna just read through this stuff here, and you have to follow these instructions. So your file has to be named adder4, okay, and lowercase add, make sure it's all case correctly. You can only use and or not gates. You cannot use exclusive or. You cannot use the half adder component in LogicSim. Yes, LogicSim actually comes with a half adder component already. That is not the point. You are going to make your own half adder. Use pins, okay, and use the label of pins to remember which one is which one. Use nested design, okay? Don't give me one huge design that has everything. So what that means is you have to create your own half adder, and then out of the half adders, you have to create your own full adder. Out of the full adders, you can finally use use those in your final design to make a 4-bit adder. The final design needs to have the following I/O, input output. You need to have A3, A2, A1, and A0 for the 4 bits of the first number. A0 being the least significant bit, and then 4 for the other number, B. 4 pins, output pins designated D for the sum, and then 1 pin designated C as the final borrow bit. Okay. In other words, if I just draw a block diagram, it's going to be this. So what you'll be doing is to first make your own half adder. Okay, I demonstrated how to make your own components on Thursday. Okay, so if you watch that video again, you will first be creating your half adder. Out of the half adders, you will create your full adder. Okay, so 2 half adders connected in certain ways, okay, will become a full adder. So if you look at this whole thing, it becomes a full adder. And then your actual design, the main design, is going to have 4 full adders. 4. There will be some connections between these 4 adders. Okay, so you will have some wires running around like this. Okay. There will be 2 input pins to each full adder. One pin that is output coming out of each full adder, but there's another one, which is this one here. This one just goes across. So that means there are 3 input pins into a full adder, 2 output pins out of a full adder. Did we talk about how to combine 2 half adders into a full adder?
Yes.
So that's basically how you combine, make use of 2 half adders and turn it into a full adder. So you will have to use 1 extra component to do it, but you also have to specify the input pins and the output pins. It's not assigned yet, okay? But I would just go ahead and start to do it, okay? Just so that you are familiarized with the tool. All right. Any other questions? If there are no questions, I'm going to stop the lecture at this point. We will be doing something in the lab, okay? So I would just work on this in the lab. If you're done with the current homework assignment already, which is pretty easy to do, I would start working on this one, okay? So that if you have questions about doing it, when you're doing it, I can answer those questions.